Hi everyone. Let's talk about the first part of the Fundamental Theorem of Calculus. This part will allow us to evaluate definite integrals using algebra. I strongly suggest that you stop the video now and attempt this exercise yourself. If you do it, you will understand and remember the Fundamental Theorem of Calculus much better. You can also download these notes using the link in the video description. In the first exercise, we are given the function capital F of t, and we are told that this function represents the position in miles of a car driving in a straight line, where t is measured in hours. We are also told that small f of t represents the velocity of the car at time t. Part A says to find the formula for the velocity. We know that the position function is given by capital F of t and equals t squared. To find velocity, we simply need to take the derivative of the position function. Velocity is the derivative of the position function. When we do that, we get that the velocity is 2t. In part B, we must evaluate the expression capital F of 3 minus capital F of 0. When I do that, I get f of 3 minus f of 0, which gives me 3 squared minus 0 squared, which is 9. Capital F was a function that represented the position, which means its units were miles. I got, as an answer, 9 miles. What does this value represent? Capital F of 3 was the position of the car at the third hour. Capital F of 0 was the position of the car at the beginning of the trip. When I subtract these two values, I get the change in position of the car in the first 3 hours. Let me write that down. This represents the total change in position of the car between time 0 and time 3. There is one more part to this problem. We must evaluate this definite integral using geometry. Then we must determine what our answer means. Let's start by evaluating the definite integral. Small f of t is 2t. I know how to draw 2t. Its vertical intercept is 0, its slope is 2. When I draw this, I get the following segment. I only drew the segment between t equal to 0 and t equal to 3 because that is the interval I am interested in. To evaluate this definite integral means to find the area of the region under the graph of this function between 0 and 3. When I do that, I get that the definite integral from 0 to 3 of f of t dt gives me, let's compute the area of that triangle, 3 times 6 times 1/2. 3 times 6 is 18, times 1/2 gives me 9. This is 9. What is the meaning of this number? If you watched my video about the net change theorem, you know that whenever you're given a velocity function, the area of the region under the velocity function gives you the displacement. A different word for displacement is the total change in position. This means that this answer is the total change in position of the car between time 0 and time 3. If you haven't seen the video about the net change theorem, I will add the link in the video description. What did we discover here? We discovered that this expression and this expression provide us with the same answer. Said differently, if you ever want to compute a definite integral of velocity, you can simply take the position function, evaluate it at 3, at 0, and subtract the two values. Keep in mind the relationship between position and velocity. Given position, the velocity is the derivative of the position function. Mathematicians realized that this equality holds not only for the position function and velocity function, but any two functions whenever this function is the derivative of this function. This is exactly the statement of the Fundamental Theorem of Calculus, Part 1. Given a continuous function f on the closed interval ab, you can evaluate the definite integral of small f of x between a and b by simply finding any antiderivative of small f of x, evaluating that antiderivative at b, at a, and then subtracting the two results. This is exactly what we discovered in the exercise above. Capital F of t was an antiderivative of small f of t, and to compute the definite integral of small f of t, we could have computed capital F of 3 minus capital F of 0. Mathematicians, instead of writing f of b minus f of a, often write f of x, then they write a vertical line, and then they write b at the top and a at the bottom. Let me show you how this fundamental theorem of calculus works in practice. Let's use the fundamental theorem of calculus to evaluate this integral. I can use the fundamental theorem of calculus here because 2x is a continuous function on the interval from 0 to 3. To evaluate this definite integral, I must find an antiderivative of 2x. I know one such antiderivative. X squared is an antiderivative of 2x. According to the theorem, I must evaluate this antiderivative at 3, at 0, and then I must subtract the two results. When I plug in 3, I get 3 squared. When I plug in 0, I get 0 squared. Altogether, I get 9. According to the fundamental theorem of calculus, we could use any antiderivative. What happens if I use a different antiderivative than x squared? For example, what if I attempt to compute the definite integral from 0 to 3 of 2x dx, and instead of using x squared, I will use x squared plus 5. That is also an antiderivative of 2x, and that is because the derivative of this expression is 2x. Let's plug in 3 and 0 and see what we get. When I plug in 3, I get 3 squared plus 5. When I plug in 0, I get 0 squared plus 5. I'm supposed to subtract the two results, that's why I have parentheses and minus sign in between. On the left, I will get 9 plus 5. On the right, I will get minus 0 minus 5. This minus distributes to both terms. Now, 5 and negative 5 cancel, and I get 9. This would happen no matter what constant we would use here, which means that most of the time, when you apply the fundamental theorem of calculus, you simply take the antiderivative where the constant is 0. If you would like to try the next problem on your own to see if you understand the fundamental theorem of calculus, stop the video now. To compute the next definite integral, I apply the fundamental theorem of calculus. The function sine of t is continuous between 0 and pi, and I get an integral from 0 to pi of sine of t dt is, I find an antiderivative of sine is negative cosine of t, and I evaluate it between pi and 0. When I plug in pi, I will get negative cosine of pi. When I plug in 0, I get negative minus cosine of 0. Remember, I must have this negative here because an antiderivative involves a minus. So this has a minus in front, this has a minus in front, and I subtract the two results. Cosine of pi is negative 1, giving me negative 1. Cosine of 0 is 1, giving me negative 1. Altogether, I get 1 plus 1, which is 2. This is a very interesting result. If you were going to draw the function sine of t between 0 and pi, this is how this function would look like. This definite integral tells us that the area of the region under the graph of the sine function between 0 and pi is exactly 2. The area of one bump of a trigonometric function sine is 2. I have one more problem for us to try. If you would like to try this on your own, stop the video now. This definite integral is very similar to the previous one. The only difference is this one starts at pi, ends at 0, the previous one started at 0, ended at pi. One way to deal with this is to use one of the properties of definite integrals. I can write that the definite integral from pi to 0 of sine of t dt equals negative integral from 0 to pi of sine of t dt. And if you don't know where this property of definite integrals comes from, I have an entire video about properties of definite integrals. I will add a link in the video description. Because this definite integral equals 2, the answer is negative 2. What would have happened if I forgot to use this property of definite integrals and I applied the fundamental theorem of calculus right away? Let's give it a try. This will give me an integral from pi to 0 of sine of t dt. I find an antiderivative and I get negative cosine of t, and I evaluate it between 0 and pi. When I plug in 0, I get negative cosine of 0. When I plug in pi, I get negative cosine of pi. Cosine of 0 is 1, giving me negative 1. Cosine of pi is negative 1, giving me negative 1. Altogether, I get negative 1 minus 1, which gives me negative 2. These two answers are the same. This shows you how powerful the fundamental theorem of calculus really is. You can use it even when this number is bigger than this number. I have one final comment. The first part of the fundamental theorem of calculus has different names. Some people call it the first fundamental theorem of calculus. Other people call it the second fundamental theorem of calculus. Others call it the evaluation theorem. If you're learning this for a class, you must ask your instructor what this theorem is called in your course.